Welcome to the titration portion of our video today. I'm going to demonstrate how to do a titration, very similar to the experiment that you're going to be conducting in lab. We're going to use the KHP that we weighed by difference in our prior video, and we're going to use that standard KHP to find out what the actual concentration of an approximate 0.1 molar sodium hydroxide solution is. And we're going to do so to 4 significant figures. Now, when we come in and we conduct a titration experiment, one thing we can do as a first step, we can do a scout titration. Now, what a scout titration does, it just takes a sample of some of the standard KHP, and we usually are going to overshoot, but we get an approximate volume as to where we're going to be needing to go for the titrations that we're going to use for our quantitative data. Another method is by calculation, and we can only do this for samples in which we're using our standard. So these can only be used when we have a standard that's nearly 100%, such as in our KHP experiment. Can't do this for an unknown sample. So I wrote down some information here on how we can calculate the approximate volume of the 0.1 molar sodium hydroxide that's going to be required to react with the 0.6185 grams of KHP that we weighed out. So in this titration, the first piece of information that we're going to need is we're going to need to know how many moles of KHP are present in the sample that we weighed out. I took the mass of the KHP and divided by the molar mass, which is given to us here, and it's going to be given to you on your procedure. And that tells us the number of moles of KHP that are in that sample. And that's going to be 0.00302844448. A few extra digits that we're going to retain. So this is a really nice, simple titration. It's what we call a 1-to-1 titration. For every mole of KHP that's present, 1 mole of sodium hydroxide will react with it. In other words, to reach the equivalence point, and that's a term that we use to describe the point in a titration for an acid-base titration, when we have stoichiometrically equivalent amounts of acid and base that react with each other. In other words, they neutralize one another. That's how many moles of sodium hydroxide are going to be required, the same number of moles of KHP. Now, to figure out the volume, we simply take the number of moles of sodium hydroxide and we divide it by the approximate molar concentration, 0.100 mole per liter. And that tells us the volume in liters. And then we can just simply convert that into milliliters. This titration should require approximately 30 milliliters. I wrote it here as 30.28. 30 is a pretty good approximation. So what we're going to do in this exercise, we're going to test our approximation by adding quickly 25 milliliters and then slowly approaching the endpoint to see where the color change occurs at. So notice I used a different term there, endpoint. There is a difference between equivalence point and endpoint. As we said, equivalence point is when we have stoichiometrically equivalent amounts of acid and base for an acid-base titration. The endpoint is the physical appearance in the environment that we see to tell us that we've reached the equivalence point. What we're going to be using today in our titration is phenolphthalein, which is the universal indicator for acid-base titrations. So let's go through how to set up our burette. Over here, I have my experimental setup. I have my burette, and I have some DI water in it. I've cleaned it with deionized water. And now what I'm going to do is add some sodium hydroxide to it. A small amount at first. And here's the sodium hydroxide that we're using today. This is called our titrant. Our titrant is what goes in to our burette. This is the glassware. And I'm going to be using my burette filling funnel. It's the small funnel with the small neck. We don't want the long neck. If it's too long of a neck, then we're actually going to contaminate our titrant that we add there. So I'm going to add just a small amount carefully. And notice down here at the bottom, I have a waste beaker. Never put your sample down there close to it because you could spill some of the titrant into your sample. So I filled up just a little bit of it because now I'm going to carefully rinse the insides of the burette out by swirling it around a little and making sure that the inside of the burette sort of gets cleansed with the titrant. And now I'm going to open this up and allow everything to flow through the burette. The burette has a nice stream going through, and we're allowing everything to drop down through the bottom, and we're going to let it simply drain all the way through so that the entire burette has been exposed to our titrant, and we've also cleaned out the bottom portion. So we're going to let that all go through, and then we're going to add our sodium hydroxide to the burette, and we're going to recognize how we read the burette. We read the burette from top to bottom. On the top, we have 0 milliliters, and on the bottom, we have 50. 50 is precisely marked. If we're adding titrant, we never go below the bottom portion. If we go below the bottom portion, it's not measurable, and we don't know precisely how much of our titrant that we've added. We also have these cards available to you in your locker. They're burette reading cards. They give us a nice dark background so we can see where the meniscus, the curved portion of our titrant, is going to be sitting at. So before I start my experiment, I'm going to fill up the burette now with the sodium hydroxide carefully. And we can add it all the way to the 0 mark. We can stop anywhere as long as we know where we originally started at. I'll close my stopcock, and I also recognize that there are no air bubbles in the bottom portion of the burette. And I'm going to add it all the way up, as most people prefer, up to the 0 point. You may have to toggle a little bit with your funnel. Sometimes a vapor lock occurs, which does not allow fluid to flow down. Now the lights went out, so maybe we could see it a little bit better. Sorry about that. So I'm almost at the 0. Again, we could start anywhere. Most people like to start at 0 because that's a nice, easy spot to start at. Okay, I'm just about there. Okay. It's a little above 0, so I'm going to lower the liquid level by opening up the stopcock and then watching where the meniscus falls right at the 0 mark. Okay, I can stop it, and I would use my burette reading card, if you can see it. I have my burette reading card right at the 0 position. So hopefully everybody can see that. Again, I'll work with you in lab as we go through our titrations. So now let's prepare our sample. I have the KHP that I weighed out earlier here in our weighing dish. And I have an Erlenmeyer flask that has some deionized water in it. I put approximately 50 milliliters. And now I'm simply going to add my KHP to the Erlenmeyer flask and slowly swirl it to ensure that it dissolves completely. Now, to make sure that we've introduced all the KHP, because there's still, I could see some specks on there, we take some deionized water, and what we do is we just squirt inside our weighing boat. And add it into our Erlenmeyer and continue to swirl it. Once it's all dissolved, we'll be ready to do our titration. One thing we do need, we need our indicator dye. Remember, our indicator dye is phenolphthalein. Phenolphthalein comes in this bottle that we'll have labeled in the laboratory. There is my KHP, almost completely dissolved. And all I'm going to do is add 2 to 3 drops. 1, 2, 3. And as you notice, it's colorless when we start our experiment. There's no color to it. And what we're going to do is the endpoint that we're looking for is the faintest pink color that we could imagine. So it's just about dissolved, and I think we're ready to go. So I place my KHP and now I can open up my stopcock and start to introduce my sodium hydroxide. Remember, we said we should be able to go to about 30 before we see the endpoint. So let's go down to 25 rather quickly to test it. And if you look at the environment there in the Erlenmeyer, eventually you're going to start to see flashes of pink occurring. So maybe I'll turn it to its side. You can start to see small flashes of pink, and I'm watching my burette start to empty. It's down to 12 milliliters, 13. Always keep swirling. 14, 15. We said 30 is about where we should end at. Get our endpoint, which it signifies our equivalence point. And we're going to go to 25 quickly. The calculation's nice usually. I'm at 22, 23, 24, 25. Okay, I'm going to slow it down there, swirl it. Notice it was staying pink, but once I swirled it, it changed back to clear, colorless. And we can always and should always squirt down the insides of that. It doesn't matter how much water we add because we know how much KHP we originally added. And it's a good idea really to keep the burette really close to there. So we're going to go down another couple drops. And notice how the pink color is starting to stay a little bit longer. And again, we're expecting it to be close to 30 to reach the equivalence point or to see our endpoint change. And once we get down here, we start going slower. One technique that we do have is to add a single drop. And what we do, I'll bring this up a little bit so you can see that technique, is we open the stopcock and we allow a droplet to form at the tip of our burette. Okay? And I just simply dab it against the side, and that's one way to add a single drop. Once you get closer, I think we need to get a little closer before we start doing that a lot. But these color changes are drastic and they can occur quite quickly. And we're getting down to like almost 27. So we're in the range now where we want to be very careful if we're working quantitatively in our lab. I'm down to 27.5. And it's almost staying pink for more than 30 seconds is what we're looking for. And we're looking for it to be very pale. And sometimes with these goggles, it is hard to see. But that's part of lab work. Got to wear goggles. OSHA requirement. Okay, we're down past 28. $28.5. 28.8. We're almost at 29. And remember to rinse the insides. Reason why we rinse the insides is some of the sodium hydroxide doesn't get into the actual Erlenmeyer. Some of it adheres to the sides of the Erlenmeyer. And real close. $29.2. We're down to 29.3. $29.4. 29.5. 29.6. 29.7. 29.8. 29.9. Oh, almost there, almost. We're right at 30, so I'm going to start adding drops at a time. And I'm going to follow that method that I was talking about by just getting a droplet and letting it go one, touching it on the side if we can, stopping it. Oh, we're so close, folks. We might be there. Nope, still not there. Squirt in some water. Oh, uh-oh. You know what? I think I'm there. Now, you might not see it, but I can tell that there's a very faint pink. Very faint. So if you get this close and you're not sure, it's a good idea to record your data. So let's record our data at this point. I would read where the meniscus is. I got 30.4. It's not quite 30.5. Actually, it is. It's like 30.5 on the nose. 30.50 is what I got. 30.50. And I would record that in my notebook. And then if we're not sure if we've reached the equivalence point, let's just add another drop. Okay, it's turned more pink. So I think 30.5 was a good indication. This is actually pink, a little more pink than what I would like. And that's still pretty good. So it looks like 30.5 milliliters is the volume that we've added. And I've used 4 significant figures. Let's return to our data. Remember, our goal in this experiment is to determine what the approximate or the precise concentration of our sodium hydroxide is. So our data told us that we have 0.003028448 moles of sodium hydroxide. The volume that we've delivered in liters, remember we said our data was at 30.5 milliliters, which is equal to 0.03050 liters. Let's calculate precisely what the concentration is. I got 0.009, I got 0.09929. So the actual concentration, 0.09929. And sometimes it's a good idea to retain one extra digit, and I usually subscript mine, 0.00929, and I saved one extra digit. Remember, it was approximately 0.1 molar. We find out precisely what its molar concentration is, and we would use that in our experiment. Hey, good luck in lab. I'll see you all on Mondays.